Okay, so today's lecture is the last lecture on phase transitions, disorder, and Griffith singularities. And as you certainly noticed, we have not touched the last keyword in the title, and that's what we are going to do today. So today's topic will be Griffith spaces and Griffith singularities. But before we go there, I think I owe you the answer to at least two questions. The first one is the answer to the little extra credit problem I gave you on Friday. What happens to the Harris criterion if you have a long-range correlated disorder, right? So remember, I asked you to look at the question of what happens to the Harris criterion if you have disorder that is not short-range correlated, but has a correlation function that falls off like 1 over x minus x prime to some power a, right? So I hope some of you at least looked at it. And if you did, what you should have found is that in the case a larger than b, so that's the case of our rapid drop-off, right? A large exponent, nothing happens, right? You get the same Harris criterion back. In this case, you still get the same, the same d mu larger than 2 that we derived on Friday, no, on Thursday actually. However, if the correlations are long-range, meaning if A is less than D, right, then in this case something changes, and what happens is that actually D gets replaced by A. Okay, so that's what you should have found, or maybe what you are going to find if you look at it now. That was question number 1. Question number 2 was the question about what happens to the two-dimensionalizing model. Right? Some of you, or at least one of you, asked this question: what happens to the two-dimensionalizing model, classicalizing model, if you add disorder? And the reason why this is particularly interesting is because this clean model has a correlation length exponent nu equals 1, and with 2 dimensions, it exactly saturates the Harris criterion, right? So it's not quite clear what's happening there. And it turns out this is indeed a controversial question, which, to the best of my knowledge, is not finally settled. So there's 2 scenarios that are discussed. One of them is that the exponents stay at their clean value, as they would if the Harris criterion was fully fulfilled. But because you are right at the marginal case, you get logarithmic corrections. So that's one possibility, and there's numerical support for this, several numerical papers whose data are consistent with this. And that's sometimes called the strong universality idea, or scenario. But there's another scenario, so-called weak universality scenario, according to which the exponents actually change slightly. And in fact, in this case, they do become disorder dependent. But it's still weakly universal in the sense that certain ratios of exponents, like beta over mu or gamma over mu or things like that, stay the same as in the clean case. And there's other numerical papers, again a whole bunch of them, whose data are consistent with that scenario. So I don't think it's fully settled. Also, my reading of the literature is that with better numerical data, the support seems to go towards the strong disorder, strong universality scenario, the first one I talked about. But that seems to be the current status. Okay, any questions? No. Then let's move on to today's topic. So for those of you who follow along in the notes, we are now jumping one section, the section on the strong disorder generalization group, because Gil talked about this at great length last week. And so we are now moving what's in the notes called lecture 4. But in our counting should be 3, right? So let's say Griffith's phases. And Griffith singularities. And the first thing I want to do is I want to simply look at the question, what is a Griffith space? Okay, so we start from again, a very simple-minded classical model. So for convenience, let's again look at the classical Ising model. and it's ferromagnetic, and so on. And so it's the simplest possible case. And of course, this is a clean system that you all know very well. Okay, now I want to introduce this order into this model, and the way I want to do it now is I want to do it by dilution. So what I'm going to do is I'm going to randomly remove some of those spins, right? And if I want to, I can do this formally by introducing a random variable epsilon for each site that can take values either 0 or 1, depending on whether or not the site is there or not. So then we get a Hamiltonian that looks like this. Right? And these epsilons are my random variables, and they can be either 0 or 1. And I need a probability, of course, in order to characterize this. So I want to call the vacancy probability. So the probability for having no spin on that side, I want to call it P, right? So this probability P, and then it's clear 1 minus P is the probability for having a site, having a spin on that side. All right. So that's my model. It's a disordered model, it's a disordered classical model. And of course we can now ask all the questions we asked last week about this model. But instead, let's first qualitatively discuss the phase diagram. Okay? So there's two parameters now that are interesting. There's temperature, or I should say the ratio of temperature and energy, right? And then there is the probability. So let's make a phase diagram in these two variables. That's temperature. That's P. And P being a probability, of course, runs between 0 and 1. Okay. So what do we know about this phase diagram without having to do elaborate calculations? Is there a few things we can say right away? Maybe you want to start on the t-axis. So what do we know there?
There will transition from order to disorder or something.
Right, there will be some TC, right? And this TC, of course, depends on the dimensionality, but we know it either precisely in the case of 2D or numerically in other dimensions. So there will be some TC. That's TC of the clean system, right? TC of the undiluted system. And we know we have a ferromagnet here and a paramagnet here. Okay, so far so good.
Are we 3D?
We are in at least 2D, right? Because I want to look at the case where we do have a phase transition, at least in the clean system. So 1D would not be very interesting because I would not be a phase transition even for zero dilution, right? But anything above 2 is fine. Okay, so now, what happens now? Now I switch on dilution, so I start randomly removing spins. What happens with my phase transition?
Along the p-axis, at some point, the vacancies will percolate, and then you have separate islands.
Right. So I heard two things that you guys said. For small dilution, I think it's intuitively clear that TC must go down, right? Because the thermal fluctuations have the same strength, while the effective exchange interaction coming from the neighbors gets reduced, so TC has to go down. That's the overall tendency towards magnetism is suppressed, so we have to start at something like that. And then, a very important observation is that there's a special dilution, the percolation threshold for the lattice, beyond which the dilution is so strong that there's no connected set of sites left, right? So along here we have the percolation transition of the lattice, and it's clear that ferromagnetism cannot survive if we only have disconnected finite size clusters, right? because each cluster will be on its own, doesn't know how the others point, so you will get a random collection of these little clusters. Okay, so we have to end up here. The ferromagnetic phase has to end here, but of course there are still several possibilities, right? It could come down before that. It could actually go like this and then come down vertically, or it could go smoothly down and hit here. And these are very interesting questions which I'm not going to discuss, right? So for now you just have to trust me that in this classical case it comes down smoothly. And you may want to think about why that is the case, but this is outside of what I'm going to do today.
Question?
Yeah?
So PC is not is less than the 2D population threshold, right?
It's precisely the 2D population threshold, right? And again, this is not an entirely trivial statement. It's not very hard to understand why it must be like that. But at first glance, it's not clear whether the two have to be the same, right? But they turn out to be the same. And moreover, in the classical case, the phase bubble smoothly comes down here. Okay, so now we have a ferromagnetic phase, now a paramagnetic phase up here. Okay? But now, let's go back to our Hamiltonian. That's a diluted Hamiltonian. And so now let's just think a little bit. These vacancies are randomly placed, right? So what that means is that there is a certain small but non-zero chance that you find a region in your system, in your lattice, that has no vacancies, right? And it can be arbitrarily large. If you just have to be lucky, right? So it's probably not very hard to find 5 or 6 close together. But if you just wait long enough and look at the large system, you will also be able to find 100 or 1,000 or 1,000,000 sites that have no vacancies close together, right? Okay, so let's assume we have something like that. Let's assume we have inside our large disordered system, we have a region that has no vacancies, right? In here, there's no vacancies. Let's assume that, right? And there's always a smaller but finite chance of finding a region like that. Okay, now let's assume you're sitting in the middle of this region, and you're starting in high temperatures in the paramagnetic phase, and you come down here.
Are you beyond PC? Or
Doesn't matter.
no?
Doesn't matter. Because PC only tells you something about the overall connectivity of the lattice, right? Even if you are to the right of PC, there you can still have these regions, right? They're just even more sparse, but they still exist. Okay, so what do you think what happens if I start at high temperatures and come down, or maybe here, it doesn't really matter. If I'm inside one of these large vacancy-free regions. It's clear that something very interesting must happen if you cross that dashed line that's sitting at TC naught, right? Because if you have a large enough region, then it looks like a piece of the clean material, right? Locally, it does not look any different than a clean system. So what that means is whenever you cross TC naught, this region here will want to order ferromagnetically, right? It'd like to. Because if we had a full system, a total system that looked like this, it would actually undergo a phase transition.
So it's already ferromagnetically ordered.
Yeah, okay. Now let's think about this, right? So can this region actually truly order? Can it undergo a phase transition by itself?
No.
Now that's a very important insight, right? It wants to do that, but it cannot. And it cannot because, as we discussed at the very beginning of these lectures, you need the thermodynamic limit to have a true singularity, right? So this cannot undergo phase transition. This cannot actually order, but it wants to. So what that means is that the spins will like to be all parallel, but the thing as a whole will still fluctuate very slowly between up and down, right? So it acts like a large superspin. Okay, let's write down a few of these things. So a region like that is typically called a rare region in the jargon of the field. So in our example, we have so far talked about rare regions where we have a small but non-zero probability of having a vacancy-free region which is then in the wrong phase. Okay, so regions where we have no vacancies, or one can actually generalize this and say we have less than the average density of vacancies. And there's a small probability of finding those, but you can find them with arbitrarily large sizes if your entire system is actually in the thermodynamic limit, right? Okay, and those regions, upon crossing TC naught, right, they want to order locally. Because they look like a piece of the clean system. As we discussed in our example case at least, they cannot undergo true phase transition because they are finite size, and we know a true phase transition requires a thermodynamic limit. And so what that means is they develop local order, the spins are locally parallel, but the rare region, the cluster as a whole, is still fluctuating, right? So we cannot undergo true phase transition. It's a finite size. But what it means, they become locally parallel and effectively act like a large superspin, right? They act like one spin, all spins are locally parallel, but the entire thing fluctuates.
Why do you think the entire thing fluctuates? Maybe some parts fluctuates, some parts doesn't.
Well,
It's also rare.
they like to be parallel, right? Because in the extreme case, you can be them somewhere here, right? So in the extreme case, it becomes particularly clear. If you are at very low temperatures but above TC, you can have there's a very small chance you can have something like this, but this would be a very strongly coupled region, which really wants to be ferromagnetic, right? So therefore, at any given time, it will, with essentially probability 1, look like that, right? But it cannot really become static because of the finite size, which means over long times it will fluctuate between up and down. And of course, you can now ask, how does this actually happen in real time? So how does it actually turn over over long times? And we have to see, if we have enough time, I can talk about this, but it's a separate question, right? If you're just doing thermodynamics, all we need to know is that it cannot be truly ordered, but it will have to be a mixture between up and down. And of course, there is some real-time process that actually achieves this, but it's a separate question.
Excuse me?
Yeah.
I would think naively that even if you're doing thermodynamics, you would have to take some sense of the dynamics into account because different size clusters are going to be fluctuating. Each size is going to have its own rate. Right. So
Yes.
the largest clusters may dominate or not dominate depending on
That's absolutely right, we'll come to that. Okay, So all this physics related to these locally ordered finite-sized clusters appears in our model here below TC naught. Right? It's clear nothing interesting can happen above TC naught. Nothing can be locally ordered. So up here we have the conventional paramagnet. Right? Give me 1 second. So this is a conventional paramagnet. Right? Because here every region in the system is just in the paramagnetic phase. Here it's still paramagnetic as a whole, but we have embedded, we have these finite size regions, and then this here would be what's called the Griffiths phase, which is slightly a little bit of a misnomer. It should be called the Griffiths region, because it's still part of the paramagnetic phase. And no symmetries are broken as you go across here. There's no different order parameters. But people like to call it the Griffiths phase, and so I'm going to stick to this. But I want to emphasize that this is not a phase in the sense that we discussed 3 days ago, right? It's part of the paramagnetic phase, which has one particular region of the paramagnetic phase. You had a question?
Yeah. So if we come very close to TC from the top, when the correlation length becomes larger than these cluster sizes,
right,
which are continuous, but there will be a subset of clusters, and the correlation length will be larger than those.
Right.
Then you can't distinguish clearly between the Griffiths phase and the conventional paramagnet, right? For those regions.
Well, I think I can, right? Because I can say, when is the first time, as I come from high temperatures, that I get a locally ordered cluster, right?
Right.
And the first, an arbitrarily large, I think that's the important key. When is the first time I get an arbitrarily large locally ordered cluster, right? And that happens right at the boundary. Yeah?
So, when you started this picture, you said this region is clean and not necessarily ordered, right?
Well,
You can have a clean system with a paramagnetic order. So when you are above TC, why should I have a phase? It's yes, exponentially small probability.
When I'm above this TC naught here, right? Then none of these regions is special, right? And
it's clean, right? That's
well, it looks clean, but from a point of view of the magnetic transition, they are not special. Because up here, I'm in the paramagnetic phase, even for the clean system, right?
yes.
So up here, you get a very conventional paramagnet that's essentially completely the same as a clean paramagnet. The interesting stuff starts to happen here once I move below, because there the system as a whole is so paramagnetic, right? We discussed this in the very beginning. But we have embedded in the overall paramagnetic bulk, we have a few very rare large regions that look like this, which means they are locally ferromagnetic and then form these large superspins.
If it's not clean, why should I have such regions?
Just by statistical fluctuations, right?
Okay.
These are random numbers, and we have assumed them to be independent.
Okay.
And there's always a small,
But
we didn't quantify this, there's a small but finite chance to have those. It's very small, but they exist. Okay, so that's my working definition of a Griffiths phase for now. The first remark I want to make is that the particular extension of the Griffiths phase is model dependent, right? Here it was particularly simple. Everything below TC naught and still in the paramagnetic side is in the Griffiths phase. But we could make a slightly different model. So the extension of the Griffiths phase is model dependent. So we can introduce this order into our original Hamiltonian in a somewhat different way, right? For instance, I could make the bonds, the interactions, random, and for the example, I wanted to make it binary. So let's say I want it to be a GA. This probability P, and GB is probability 1 minus P, and for me, GB is actually larger than GA. And of course, it's no importance. Okay, so what phase diagram do we get in this case? Same game, temperature up here, probability down here. If we start at P equals 0, we have a system that contains only the small ones, right? That means we have some critical temperature that I can call TB. So that's the critical temperature of a hypothetical system, or let me stick to the notation of my notes, it's TCB. That's the critical temperature of a system that contains purely out of strong B bonds, right? On the other hand, in this case, if you now go to P equal 1, and we don't go to 0, right? Because over here we still get a non-zero critical temperature, now again of a hypothetical system that has purely A bonds, right? So which is somewhat lower. So let's say here, that's TCA, right? Well, then we somehow have to interpolate between the two, and I don't want to focus on how that exactly goes, some curve between the two, right? And below, it's all ferromagnetic, and above, it's all paramagnetic. But now you see there are two special lines that we can talk about, right? One line plays the same role as the line up here. That's this line here, right? So if you are up here, we have the conventional paramagnet, every part of the system is paramagnetic. Then if we cross down here, we are in the Griffiths phase, right? Because now we can have large regions that have more B bonds than the average. And again, they form these superspins because they locally look like a piece of the clean B system. We already see it looks a little different, right? But moreover, we can now go further. We can actually say, well, if this is special, what about the other line we can draw? Right? The line that is horizontal at TCA. What about this line? So what's the difference between being here or here? The system is ferromagnetic in both cases, right? But somehow we expect there must be some difference, right? And this, along the same lines, there's a difference here.
Get arbitrarily large, non-ordered phases, non-ordered clusters.
Yeah, you get holes, kind of, right? You get arbitrarily large holes inside the ferromagnetism, because if you're over here, the system is all ferromagnetic, but there may be a region that has too many A bonds, weak bonds, right? And then this forms a hole inside the ferromagnet, right? So that's, if you want, the ferromagnetic counterpart. And people typically call this a ferromagnetic order, whatever your other order is, the order of Griffiths region, and this is the disorder of Griffiths region. So the use of language is not entirely unique. If people say just Griffiths region without an argument, they typically mean the one on the disorder side. But there is a counterpart that you can clearly see here. That's the ordered, or in this case, ferromagnetic Griffiths region, right? Question?
What justifies you in treating these as two kind of disconnected regions, an A region and a B region, and ignoring the boundary?
I have not made any.
Sure, you're assuming these lines are kind of flat across, which is to say that the rare A regions really just look like A.
Right.
You don't have any remnants of the B boundary that's sitting around.
Oh, yeah, sure, but if they're large enough, right, then you'd expect that the boundary effect should be subleading.
Well, you'd expect
Yeah.
that to be dimensionally extended as well. So
Sure, yes,
yeah,
yeah. But since we are above 2 or above, right, naive counting tells you that for large enough ones, the boundary should play a subleading role, right? It's something one should think about if you want to do the actual calculation. But for our hand-waving arguments, I think the naive expectation at least would be that they shouldn't melt. So then this is the ferromagnetic surface space. Okay, it's probably worth pointing out that the symmetry between the two is not perfect. Let me explain why. In the paramagnetic or normal Griffith phase, we had these superspins, right? We had these rare regions that formed the superspins, and it's important to realize that they are interesting because they actually carry a separate degree of freedom. And they can be up or down, and therefore there is physics connected to them, either classical dynamics, thermodynamics, or even quantum dynamics in the case of quantum phase transitions that we will talk about in half an hour or so, right? So there's a separate degree of freedom attached to these rare regions. In our simplest case, it's a binary one, up or down, right? Now, if I make a hole, as you correctly pointed out, there's no such thing, right? So, if I make a hole, maybe over there, if I make a hole into the ferromagnet, then I have no extra degree of freedom attached to the hole. Okay, so let me see how do we want to draw this picture. So out here, I have outside I have the ferromagnet, right? That's a typical region, which means we are in a B-rich region that's over ferromagnetic, right? All right. Now we have a hole, which means inside this region we have too many A's, right? Too many weak bonds. So that's an A-rich region, which means this is locally in the paramagnetic phase. So it's a hole in the ferromagnetic order, right? But as I said, there's no degree of freedom, right? There's nothing that we can do here. So that means it's not quite the same as in the paramagnetic Griffith space, where you have this degree of freedom attached to the rare region. Now, if this was actually all, this would be a very boring region, right? We would have a few holes, but otherwise nothing interesting would happen. So, then you see a way to bring back at least something of the physics of these superspins we talked about. Right? So far we don't have it, right? We have a more or less uniform ferromagnet on the outside, and we have the hole in the inside.
Maybe you can think of the hole as superimposing opposite spin on a uniform background or something.
I think that's the right idea.
You can put another violet inside the hole.
That's a key idea, I think, right? There may be regions like this in your system, right? But they are boring. There's no dynamic degree of freedom attached to it. But there may be others. And the others may look like this. Now you have inside the large A-rich hole, you have a smaller B-rich region, right? That means this region now, again, wants to be ferromagnetic, right? But because it's isolated from the bulk ferromagnet by this hole, right? It can individually flip, right? It's not really, it's only very weakly coupled to the bulk because you have the paramagnetic region in between, and this again gives you the binary degree of freedom that will lead to interesting physics in a few minutes. Okay, so this is the physics of the ferromagnetic Griffith space. It's produced by regions like that, right? And since the geometry is a little different from the paramagnetic side, all the actual results that you will get are not quite fully symmetric. right? They are similar, but not quite the same. Question?
Does this somehow continue in some fractal kind of way, or you terminate at level 2?
No, of course you could continue it, and you probably would have to think about probabilities for this to happen. This is of course already much rarer than a hole by itself, right? But since this is the first time you get something interesting in this hierarchy, that's probably the leading term, right? But of course, in principle, there will be regions, some even rarer, that have another hole, and then another hole, and so on, right?
What's confusing is what you're calling a hole. It's sitting in the Weiss field, or in the external field of the D-rich region outside.
Right, exactly.
So it would not polarize it to
yes,
the extent that
it will weakly polarize it, right? So this is, of course, in our example, this will not be truly magnetization zero in this region.
Right.
It will be weakly polarized, and what you need, of course, is that the extension of your hole is larger than the correlation length of the paramagnetic inside, right? So depending on where you are in your phase diagram, you need a certain minimum size of the holes for the physics to be correct, right? But since we can have arbitrarily large of those, in principle they are always there, right? Okay. Any questions about this? So if not, then of course the next question is, why is this interesting, right? So far we have just established that something like this must exist. So we know if you have a dirty ferromagnet, or generalizing this, some dirty system undergoing a phase transition, then generically you will have these Griffith phases around the actual phase boundary, right? Here, or here. By the way, where's the ferromagnetic Griffith region in this phase diagram? Do we have one?
Sure.
That entire phase.
It's the entire ferromagnetic phase. There's no conventional ferromagnet here, because no matter where you are, you can always punch holes, right? You can always punch holes that are completely paramagnetic. So here, the entire ferromagnetic phase is all Griffith phase. There's no conventional ferromagnet below as we have here. Okay, so we've established that we will all have these Griffith spaces around the phase boundary, but I have not discussed why you should care, right? Well, when they are there, so let's see what they do, okay? And there's actually an interesting history to this, because the field goes back a long time, more than 40 years. It was in 1968 that Griffiths, who gave this thing the name, he actually showed in a mathematical formal proof that whenever you are inside one of these Griffiths regions, the free energy is a singular function of the parameters. And this was hotly discussed at that time, because it's not what you normally have. We discussed at the beginning of these lectures that singularities in the free energy very often, if not almost always, signify phase transitions, right? But he proved that you get singularities not just at a particular point or line in the phase diagram, but in an entire region, right? But his proof was a formal proof, and at that time it was not at all clear what it means physically. And what I told you already, so far is already going beyond that. And then in the 70s, people actually developed these ideas and understood how they are connected to Griffith's proof. But it turned out, and I will show you in a minute, that for classical systems like the one we have just looked at, it's mostly uninteresting because it's probably not observable in experiments. And then the field lay dormant for a long time. And it only came up again in the last 15 years or so, when it turned out that for quantum phase transitions, you get actually much stronger physical effects that are measurable. Okay? So what I'm going to do now is I'm first going to talk about the effects of these regions in the classical system. And we will convince ourselves that they are there, and they actually indeed do lead to singularities, but they are probably unobservable. And then we move on to quantum phase transitions, then we will see they are even stronger, and strong enough to actually lead to observable effects. Okay, so that would be now 3b, if I'm not miscounting. Classical Griffiths singularities. Okay, and so let me just write down what I just said. Griffiths in the year 1968 gave a formal proof showing that in a disordered system, and of course there's conditions which I'm not spelling out, it's a real rigorous result. He proved that the free energy is singular not just at the phase boundary in a disordered system, but in an entire region around it. So free energy is singular function of external parameters, not just at the phase boundary. But in the finite size region of the phase diagram.
So does that mean that some derivative is not defined?
We will actually see how they look like, the singularity, in a minute. Yes, that means some derivatives are blowing up, right?
So how would you then define, I mean, how do you then see the, like, what is your phase transition?
Oh, very good question, right? So how do I find out if everything is singular everywhere here, right? So where's my phase running? How do I fix this? Suggestions?
Some order parameter? Or?
Exactly, right? The order parameter here is 0, right? Where is here is not 0.
What's it?
The other way around, sorry. So in the ferromagnetic Griffith space, the magnetization, which is the order parameter of this position, is non-zero. Up here, it's 0, right? So that defines what the phase boundary is. Okay, so to understand where these singularities come from in a physical way, so that's not what Griffiths actually did, but to get a physical feel for what they are, what we can do is we can simply try to estimate in the roughest possible way the contribution that these rare regions are making to some simple thermodynamic quantities. That's what we're going to do now.
So can I ask you a question about this model that you're erasing?
Okay, sure.
So when you take the limit of JA going to 0, this TCA will go to 0, right?
Right.
But it seems that the line will go all the way up to P equals 1, right?
Well, it probably gets steeper and steeper here, right? And in the limit, you actually get a sharp peak here.
Okay.
Right? Because in the limit j to 0, as you imply, I assume, you get the other model back, right? So the only way I can think of this happening is that this becomes sharper and sharper here.
It's slightly different because you're removing bonds, right?
Right, but this is just a quantitative difference, not a qualitative one. In the one case, you have a side percolation picture. In the other case, a bond percolation picture. But the only difference from this point of view is that the thresholds are slightly different values. The qualitative behavior is the same. Doesn't matter what you remove. Okay, so let's try to estimate the contribution of a single of these rare regions to, well, let's say to the magnetization in a field or to the susceptibility. These are two simple things you could do. And let's assume we are in the paramagnetic Griffith space, the simple Griffith space, and let's see what they are doing. Estimate contribution of the single region to M of B and chi of t. That's what I want to do. Yes. In paramagnetic space. So if I want to talk about M of B, of course I need to add a magnetic field to the Hamiltonian. It's done in the usual way. So just for completeness, let me write it down again. Right, so you have the usual linear coupling is the field and the spin, but of course the spin has to be there, otherwise there is no field shown. Okay, so how can we estimate the contribution that a single layer region makes to the magnetization in the field? So let's orient ourselves a little bit, right? So we are in the paramagnetic phase. In this picture would be here, and the other picture was the entire thing, right? And the paramagnetic phase. So the first thing to think about maybe is the bulk contribution, right? As we discussed, in this paramagnetic Griffith space, we have a paramagnetic bulk, and then a few rare large regions of the type we discussed, right? If I now switch on the magnetic field, maybe the first thing to think about is how will the bulk respond?
What was your question?
Well, if we switch on a magnetic field, right, we want to discuss the magnetization as a function of the field. There will in general be two contributions. There will be one coming from the bulk system, right? So how will this depend on the magnetic field?
Q relay.
If we are somewhere in the paramagnetic phase, linear, right? Simply linear response. If you are in the paramagnetic phase, the bulk will have a very simple linear contribution characterized by some bulk susceptibility, right? So that's not the term we are after, right? It's clear there will always be some linear in B background, right? Question?
So I don't understand. It looks like if you're in the bulk, you're completely separate from the field, so that there's really no contribution at all. Because you have the epsilon i's on the B term.
Why would I don't see a field response? I mean, the field happens to all the spins that are there. Whenever you switch on a field,
The temperature's higher, but still.
it doesn't really matter where I am in the phase diagram, right? There will always be some linear response of the spins that are there to the field, right? Characterized by some susceptibility that I could write down. But as I said, this is not the term we are after, right? This is certainly not leading to one of Griffith's celebrated singularities, right? It just gives us a linear response term. Okay, so now let's think about our rare regions, right? And we are somewhere here, right? So we are in the phase, in the Griffith space, where they want to be ferromagnetic, right? So if you have a region that wants to be ferromagnetic, right? It wants to be, and you apply a small field, what happens to this region? It aligns, right? So the basic idea is that large enough of these regions, they will essentially perfectly align with the field, right? So how can we decide how large they have to be to align with the field?
The gain has to be larger than the band.
secondary energy?
Uh,
The correlation then should be larger than the.
Yeah, so that's good ideas in both what you say. So we need to compare the energy gain from the field with something. Temperature, right? Because it's a final temperature phase transition here, right? So the energy gain has to be larger than the thermal energy. So larger region aligns with the field. If, and now we want that kBT, the thermal energy, has to be less than the energy gain due to the field.
Shouldn't we do an entropy calculation? Because that's what.
I mean, we probably should do a free energy calculation, but I don't think it makes a difference here.
Okay.
So what's the energy gain in the field? Look at this term. How much energy do we gain by aligning with the field?
NG.
Be the area.
Yeah.
E times area.
Your volume, right? Whatever. B times the volume of the rare region, right? Because each spin in the rare region will contribute to B. So let me see how do I want to write this. Yeah, let me simply write volume, and I measure volume in terms of unit cells, right? Okay, and the smaller ones, they don't want to align with the field, right? Or at least not strongly enough, and they will essentially just make a contribution to the linear response term, right? They are not fully aligned, they are fluctuating around, and they contribute to the non-singular part. So what we need to do to estimate the singularity, if there is any, don't know yet, we need to sum over all of those, right? If we sum over all of those and fulfill this, we get the contribution of the special regions, right? Those that behave differently from the bottom. So let's sum over all of these regions.
So Thomas?
Yeah.
Shouldn't we be saying that the linear scale of the region should be larger than the correlation length at that point? Especially since we are below TC, shouldn't we be thinking that way instead of like this?
I'm sure you can probably think in this way and arrive at the same result. But maybe you might discuss it after that, right?
Yeah, he's going to take the limit of large volume, so that will be true. At least I think so.
Yes, you're full right.
So
They-
why,
Another question?
why do you have epsilon I in magnetic fields?
Because there's only a coupling between the field and the spin if a spin is there, right? Remember, this was just telling you whether it's a vacancy or not, right? Okay, so to get the total region contribution, I can now, in order to make a rough estimate, I can now simply sum over all of those, right? All of them fulfill this. And the basic idea behind this is that they are so rare that they are far apart and therefore effectively can be considered independent, right? They don't talk to each other. And in this case, then the total region magnetization can be estimated as being an integral over volume, right? All the possible sizes. This gives us a lower cutoff, right? They have to be large enough to fulfill this. So that would mean V has to be larger than kBT over B, right? Whoops. Yeah, so V has to be larger than kBT over B. And we can go all the way to infinity, right? Okay, now what we need two more things, right? We need an estimate for what's the contribution a single one makes to the magnetization in this case. But we discussed it already, right? The magnetization of a single of these regions is essentially the volume, right? Because the number of spins in the region is proportional to the volume. And then, importantly, we need an estimate for the probability of finding one, right? So far, we just waved my hand and said they're very rare. So we need some, let me see what simple field I want to use. Some W of V. W of V is a probability for finding a region. of that volume. That's the probability for finding a region of volume V. So, what about this function? What do we know about this? It's exponentially small. So for this model, we can actually be slightly more explicit.
B to the B.
The probability for finding a vacancy is P, right? So the probability for finding no vacancy is 1 minus P. So it's 1 minus P to the number of spins we want in the region. And then there's a combinatorial prefactor, of course. So it's something like this, and there's a combinatorial prefactor. But if I'm only working to exponential order, I don't have to care about the prefactor, right? And of course, this is e to the minus, let's call it p tilde times v, right? Okay, so now we are in business, right? Now we have something we can actually calculate. We have to integrate dv v e to the minus something times v. Okay, and it's clear, since I'm only working to exponential accuracy, I can drop the v here actually, right? Because there will be power of prefactors in front of that anyway. So whether or not I keep the v will not change the result to exponential accuracy. And if I do this, then of course it's a trivial integral, right? It's simply an exponential integral which you can carry out right away. And then the result I get is e to the minus a lower bound, right? E to the minus kbt over b. Say again? P twiddle. Thank you.
Can you remind me what P typical was?
This was the constant I get from rewriting the combinatorial result in exponential form, right? So it's minus log of 1 minus p, right? P twiddle is minus ln 1 minus p. Question?
So when you write down the criteria, I think you need to use the central limit theorem, right? So this should be b times the square root of v at least, because kbt is for each single particle, right? And bv is the total energy. So I think
no, I don't think you're thinking about this in the right way, right? This region we are looking at is fully polarized, so the spins are perfectly parallel, and it has only one binary degree of freedom. It can be up or down, right? And we need to compare the energy difference between the up and down states with the thermal energy, right? And the energy difference between the up and down states is of the order of b times v. There's no square root here because they're all parallel. And I'm not using central limit theorem. They're all perfectly parallel, and therefore their energy is either plus or minus b times v, depending on whether or not the entire island as a whole is aligned or anti-aligned with the field.
But I mean, the kbt is for each single degree of freedom, right?
Yeah, but this is a single degree of freedom, right? Because we are in the Griffiths region, the interactions already force all spins to be parallel. And then there's only one single degree of freedom left. They can all be parallel and up, or they can all be parallel and down. Right? Well, okay, so that's the result, right? So here you have your singularity. So what we see is that indeed, as predicted by Griffiths' formal proof, the magnetization is a singular function of the field, right? It's e to the minus 1 over b. It's a singular function. It's not linear response. So that means this estimate is in complete agreement with Griffiths' prediction, That's the first observation, right? There's an essential singularity in B. But you also see that for small fields, this goes to zero extremely rapidly, right? And that's the reason why the general conclusion is that these classical Griffith singularities are probably not observed in an experiment. And people in the 70s actually made some estimates and found out that from an experimental point of view, the effects are too weak. Even though they are there, they cannot be seen in classical systems.
So this is added on to the linear response?
Yeah, in the most naive estimate, you would add this term to the bulk term, right?
As a coherent one.
There's a linear response bulk term, and then there's an additional term coming from these, but it's too weak, and it's completely buried by the bulk term.
Could you maybe explain why the result is so non-perturbative in B?
I think the result comes from the fact that these fully polarized, right? There's nothing perturbative about this, right? These regions, if they're large enough, they fully polarize in essentially arbitrarily weak field. They're large enough, and that's where the non-perturbative character comes from, right? It's already here, right? It's already non-perturbative here. Okay, just for completeness, we can also estimate the susceptibility. And this will be interesting because we can contrast this with the quantum case, which I'm going to start in a minute. So now let's actually ask a slightly different question. Let's ask about the susceptibility. And you make the same type of estimate. I'm going a little faster now, same ideas. So what we need to do is we need to find the susceptibility of a single one of those variations, right? Chi of V. So what should I write down for that? And in the paramagnetic Griffith space, it's the paramagnetic bulk, but embedded I have one large superspin, right? What's the susceptibility of this superspin, the single one? Right? It's a classical superspin, so we can immediately write down what it is.
1 over T.
It's 1 over T, okay. T, that's good. I need to bring in the size, right? Clearly the value will depend on the size. V squared, right? Because as you undoubtedly remember from your StatMech class, it's moment squared over T, right? And the moment is proportional to V, so it's V squared over T, right? And then we do the same type of integral, right? Now, if you want the total region contribution coming from all those regions, then that's the total region contribution chi R is proportional to integral dB W of V and chi of V.
So I have a question.
Yeah.
Why can't I just differentiate the magnetization with respect to B?
It's essential singularity, right? So the derivative will vanish at B equals 0.
I see.
You never get a divergence, which of course is one aspect that tells you it's very hard to observe, right?
So
never blows up.
So the curious susceptibility doesn't come from the change of this magnetization, but probably from the change in the lower bound of the integral?
No, see, here you see, if you look at the result, that only the lower bound contributes, right? That's a finite size,
Right.
and the finite size of the region over there have some finite curious susceptibility.
Right.
But now here you can make a similar argument, right? It's clear that here we have a V squared, but we have an exponentially decaying function of v, right? So therefore the exponential wins, and there's no large contribution coming from large area regions, right? It will integrate to something, but it's not interesting because the large area regions, which are the ones that we hope do something, they are too strongly suppressed because chi of v doesn't integrate, doesn't increase fast enough as v. Right, so this integrates to something, but there's no divergence coming from here. And again, you get an essential singularity coming from the exponential there, but nothing that would blow up or make a large contribution.
It's just pure, it's still pure.
The temperature dependence based on that estimate will still be purely, right? But the crucial point is that this is again a small extra contribution to the large bulk contribution, which is completely buried because it doesn't stand out, right? So large regions make a small contribution. That's the crucial conclusion. Large regions make a small contribution. Okay, and therefore the upshot of all of that is that there are regions, or I should be careful and say should say the thermodynamic behavior of their regions is very likely to be unobservable in generic classical systems. And of course, it's a very sweeping statement. It turns out that it's of course not rigorously true. There are cases where you can observe it in classical systems, particularly if the disorder is long-range correlated, but I'm not going there for the moment, right? Moreover, it's important that I said thermodynamic here, because if you look at classical dynamics, so if you come back to the question of how the variation actually turns over in real time, and for instance try to calculate real-time correlation functions, then it turns out that variations can actually dominate the long-time behavior, even for classical systems. I think it's written up in the notes, but in view of the time, I'm not going to discuss it. Let me just make the remark that it can be different for classical dynamics. And there are, for classical dynamics, so classical time correlation functions, there are actually experimental results that are in agreement with the predictions that you get if you do that. Okay, question?
Sorry, just very briefly, is there some interesting behavior in like the noise or something? Do you want to grab noise or something coming out of these?
Probably not in these generic classical systems, because everything is exponentially suppressed. But there will be very interesting things in the quantum case that I'm going to talk about now.
So there is no experimental signature for this?
These results that we've discussed just now are probably too weak in terms of amplitudes to be seen above the bulk contribution for M or chi.
But you have a signature in dynamics.
But you have a signature of the variations in the classical dynamics, right?
What is it like?
Well, if you look at the other correlation function, it does show non-exponential decays. And you can actually calculate the functional forms and compare them with the experiment. And this has been done, and there are some results that confirm these predictions. And again, there is a section in the notes, but since I really do want to talk about the quantum case, I'm skipping this for now. Okay. So, as you've seen, not much interesting going on here, at least in thermodynamics. That's why the field was dormant for about 20 or 25 years after people realized that it's maybe interesting from an academic point of view, because you get singularities, not just at equality point. It's maybe not so interesting from an experimental point of view, because you just cannot see it. But then when people started thinking earliest about quantum phase transitions, the field became active again, and we will now see why. Okay, so that's 3C. Quantum versus singularities. So that means we now have to look at the model of a quantum phase transition. And what I want to do is I want to use transverse field Ising model as an example. So the same model that Gil was talking about on Friday in one dimension. I want to look at the higher dimensional version and put in dilution just as we did before. Okay? So transverse field Ising model. So you've seen the Hamiltonian probably several times. So if you see, I want to call the transverse field H. It's called Hx to make absolutely sure you don't mix it up with the B field over here. Right. So that's the transverse field Ising model that you have seen. And all I've done is I've actually added my random variable epsilon to introduce dilution. Right? So epsilon plays the same role as it did in the last section. It can be 0 or 1 with probability p minus 1 minus p. So it's side diluted. Okay, and the first thing we probably should do is we should talk about the phase diagram quickly, right? So now I want to look at the quantum phase transition. So instead of tuning by temperature, I'm tuning by tuning the magnetic field here, right? The transverse field. And on the x-axis, I have dilution as before, between 0 and 1. Okay, we already know, probably have to think about the percolation threshold somehow. Did play a role in the classical case. So now let's fill in the phase diagram. So let's start with a clean case. So what should I do in the clean, on the clean side, on the y-axis here? There's some critical value for the transverse field strength. Let's call it HC0, in analogy to the TC0 that we had in the classical case. Okay, so then what happens if I not dilute the system? What happens to the phase transition? Where does it go?
Go down. Goes down.
Which way? This way? It has to go down again, right? I think it's using the same intuitive insight. The field doesn't change, which means that the source of fluctuations doesn't change, but the overall interaction changes, so it has to go down. And we also know it cannot go beyond PC, right? Because at PC, your underlying lattice falls apart into independent clusters, so it's clear ferromagnetism cannot survive. So it has to go down somehow, and then it has to end up here. But it turns out in this case, the phase diagram is actually different. And as I said, it's interesting, but I'm not going to talk about this. It turns out in this case, there's actually a special point somewhere here. and it looks like this. So the magnetic order survives at PC. It did not survive at PC in the other case. So you may want to think about this if you have a free minute, but I'm not going to talk about this further. In any case, for our purposes, we can now make the same arguments, right? I can draw this line here. And now this gives me a Griffith space, right? Because if I'm up here, no matter where I am in the sample, I will always be paramagnetic, right? So up here, that's a conventional paramagnet. Down here, I'm in the ferromagnetic phase. And here, that's paramagnetic or conventional Griffith space, right? This is Griffith space where I have a paramagnetic bulk, but embedded possible rare ferromagnetic regions. And as before, the ferromagnetic phase here is in fact a ferromagnetic Griffith space, all of it, right? So that's not different. Okay, so now what I'm going to do in the last 15 minutes or so is I'm actually going to go over the estimates again. And I'm trying to convince you that in this case, actually, we get large contributions from the rare regions if we are sitting somewhere in the Griffith space, right? And that's why they are observable. And to do this, we first need to think about a single rare region. And of course, we now need to think about it quantum mechanically rather than classically, right? Because it's a quantum problem. So that's my rare region. And I'm just drawing these arrows to remind you that it's a vacancy-free region, right? Okay, so now let's look at a single one of those rare regions, and let's say we are over here, right? They're deep in the Griffith space, which means we are overall paramagnetic. The underlying bulk is paramagnetic, but the field is way too weak to actually destroy the local order here, right? So now, one thing we can think about, it's very useful, is to think about the energy spectrum. What's the energy spectrum of this rare region? You know the Hamiltonian. Let's just look at the region by itself. What's the energy spectrum? It's doubly degenerate, yeah, almost, as we will see. So which are the two low-lying states that you're thinking about? All that, right? It's clear that this is what the system wants, right? Because we are deep in the Griffith space, so the interactions are much stronger than the fields locally. So the spins want to be parallel. Right? That means we have two low-lying states, and they are formed by all up and all down, right? Okay, what about the other states? There's many more states, right? This thing has totally 2 to the n states, right? If you have n spins in there. Where are they in my spectrum?
There's a gap G.
There's a gap. So how large is the gap? Order J, right? So why is the gap order J?
Living with cost energy.
Right, because if you are not in one of those two states, right, then you will have at least one pair of spins that are anti-parallel, right? And this will cost you a J, right? So there's tons of states up here, but there's a gap of order J, and then you have these two low-lying states, right? Now, you said they are degenerate, right? Are they truly degenerate? Right? They would be truly degenerate if you didn't have this field at all, right? So on that line down here.
But they're really hybridized, huh?
But they weakly hybridize, we'll estimate in a second how strongly, they weakly hybridize because of that, right? And that means they're actually not degenerate, but we get a tunnel splitting of that type, right? And so there's a gap between these two. I think I want to give it a name. Epsilon. Well, that's not good. Let's call it delta. Let's call it a little gap delta. Capital delta. Okay? And it's clear that all the low energy physics that's responsible for the quantum phase transition, of course, will live up this delta, right? It's clear if I have low enough temperatures, these states up here will not play a role, right? And of course, that's just the quantum expression of the same idea that what this variation is doing, it's either all up or all down, and tunneling between the two, right? Whereas all the other states, they are suppressed. Okay, so now in order to make this a quantitative argument, we need to estimate the splitting here, right? Okay, so any ideas of how we could achieve that? Any idea of how large the splitting is between these two levels?
H to the power n plus 1 by j to the power n.
Okay, so I heard something like the correct result already, but so where does it come from? Okay, so perturbation theory, right? So we could try to do the perturbation theory, which will certainly be good down here, right? And we can hope that it will remain valid up here because nothing interesting happens along the line, right? So let's assume we are down here where h is small, let's do perturbation theory, okay? That's a different type of talk. Okay, so what that means, what we need to estimate are matrix elements between the all up and all down state, right? To do perturbation theory. Something like that, right? And these matrices give me an estimate for the tunnel splitting. Okay, so now let's just go ahead. First of all, it means we have to put this in between, right? So what do we get? Yeah. Why do we get 0? Right, because each of these terms can flip just one spin, but we have a large number of all the V spins in here, right? So then we get 0. And now it's clear what you need to do, right? If you have n spins in your region, it means you need to go to nth order perturbation theory before you can actually flip all spins and get a non-zero matrix element, right? So it means we have to put hx sum over I epsilon I as ix to the power of n. Yeah, n is the number of spins in the region, right? All lower terms are 0 because you never get an overlap. And that's a very interesting result because it tells you that this gap here is actually exponentially small. It's a crucial insight. It's exponentially small in the volume of that region, right? And of course you can now actually fix this up and put denominators, but for the argument it's all unimportant, right? The basic result comes from here, And that tells you that the gap delta of V must be exponentially small in B, right? And I don't want to work out the details, I just introduce a constant that contains all of that. That's HI, so hx to the n, which I'm writing as e to the minus a times v, right? Because the number of spins equal to the volume, I can write it like that. And a contains all the constants. Okay, so now why is this interesting? Well, you see, why it's interesting if you now try to combine this with the probability for finding a region. So one way to proceed is to actually now calculate the density of states for the rare regions, right? We have an energy and we have a probability, and if we can combine them, we can calculate the distribution of energies, which is nothing but the density of states, right? Density of states of the rare regions. So how would I do this? Rho of epsilon would of course be an integral over all volumes. Then we need the probability from the last section. And now I need to transform to epsilon because I want to get a rho of epsilon. So I need a delta of epsilon minus that, right? And it's not epsilon, it's delta, of course. Sorry about that. Rho of delta, delta minus e to the minus a times v. Okay. And that's something that they can immediately carry out, right? The trivial integral. And the very nice result is that the two exponentials combine to give you the power. Right? So I leave the actual calculation to you. So what you get is e to the minus delta to the p tilde over a minus 1. Okay, so we get a power law density of states, and in particular, you see that the density of states can blow up, can diverge, if A gets very, let me see, A gets very large, right? Right? If you look where A comes from, it means if the field gets small, right, then you actually get a diverging density of states. So that's a much stronger effect than we had seen in the classical case. And of course, we can now calculate observables the last 3 minutes to actually confirm this, right? Just to introduce a notation that's used in the field, people typically parameterize this exponent here. It should be proportional here. Proportional. They parameterize this in terms of a dynamic exponent. So this p tilde over a, which is some non-universal number, gets parameterized in terms of d over z prime, where z prime is the so-called Griffiths dynamic exponent. And of course, at that stage, maybe not completely clear why this is actually called the dynamic exponent. But what you can do is you can simply calculate how many rare regions you have below a certain energy, and then calculate the typical distance between them, just from their density. right? And then you get a relation between energy and length. And then you will see that this is indeed governed by this exponent. So this is not just a name, it really means, has the same meaning as a dynamic exponent in other cases. Okay, so let's calculate at least one observable, maybe two, and then I stop. And the first one I want to do is,
question in the
Yeah.
last section. Is it important to take into account the absolute value of the energy rather than just the gap to see how, I mean, when we call it density of states, to see how the states are actually distributed? And then we say that that's not, how that also depends on volume?
yeah.
Is there
No. What you want to write down, particularly if you want to later on calculate observables, is the distribution of the gaps, right? Now the absolute zeros doesn't really matter. What you need is the distribution of the energy gaps of the different regions, right? And that's what you actually calculate.
Maybe a similar question. What sets the upper energy scale where this power loss in a whole?
Well, there's various possibilities for cutoffs. One, of course, is J, right? Once your energies become of the order of J, then at the latest, this will still change, right?
I mean, the highest energy can only be 8. Right.
Okay.
Is it also cut off by the correlation line? The following correlation line?
Well, if you approach the boundary of the Griffith space, and then let's say going up in H, right? Then you may wonder how this goes away as you approach that boundary. But if you're deep inside the Griffith space, your correlations are essentially perfect on the locally ordered region. So I don't think that plays a role.
So the maximum limit on the gap should be something like 8 squared by J, but not J. That's just a Griffith region with 2 sites.
Yeah, maybe.
Which is, it should be indistinguishable from the rest.
Could be, yeah. That's the word several. Okay, let's calculate chi of t. Because that's something that experimentalists can easily measure, right? They cannot really make an experiment at 0 temperature, but they can measure the susceptibility as a function of temperature in the vicinity of the quantum phase transition, right? So I want to estimate a radiation contribution. Well, how can we do that? What we know is the distribution of gaps, right? How can we estimate the contribution that the regions make to the susceptibility?